So good afternoon, everyone, and welcome to this webinar. I'm very pleased this afternoon to introduce my colleague, Michael Berford. Michael is going to talk to us on 4 separate topics this afternoon, a series of lightning talks, all related to code performance on our services ARCHER2 and on Cirrus. So if you'd like to get set up now, Michael, and away you go.
This is my title slide. My name is Michael Berford, as Claire said. So I'm going to just present a series of lightning talks, each one taking between 5 and 10 minutes. And there's not particularly much overlap between them. They are loosely together. They're concerned with the topic of code performance, how to ensure that your code performs at scale. If there's a complicated software stack involved, how to make sure that that is performing when you run across multiple nodes, how to evaluate the different elements within your code, subroutines, functions, and so on. And then lastly, how to take advantage of accelerators, GPUs, which is something that is going to be more useful to people as GPUs become a more common part of HPC systems. Right, so the first lightning talk concerns Spindle, which is a means to improve the library load performance of codes when you run them across many nodes. And this is of particular relevance to Python codes, which are becoming quite common on HPC platforms. And the way these Python codes are used, there's a Python front end, basically, within which the user can describe their model. They can describe the mathematical equations that underpin their model. And then the Python code will then interpret that into a set of computational kernels that are compiled for the native, the actual environment, so that they perform well, and you have something that's going to be performant. When you start to run Python on a large core per node machine like ARCHER2, where you have 128 cores per node, and if you go out to say about 100 nodes, you have potentially over 10,000 ranks. You can have this issue where each of your ranks are working through the same Python script, and they're working through the same set of import statements. And then for each of those import statements, there's a potential lookup for a library that will involve searching through a number of different folders. And so all of this can be a huge hit on the Meta IO server. So this will slow down the performance of your code, the time it takes to start up. And also it's going to impact the performance of other users running their own jobs, because everyone's sharing the same Meta IO server. The nice thing about Spindle is that it can be used in a way where you're not required to change any of your source code. You're not required to introduce any special compile options. You can just basically indicate that you're using Spindle within your submission script. So it's nice and separate from your actual code. So this is, I'm just going to talk about how Spindle is built. If you're needing to build it on another HP system that you might have access to. And really it's a straightforward configure, make, install. All of the action is in the configure command. And you have a few options there. The enable sec none, the sec refers to the security model. And that is set to none because when Spindle runs, it will be confined to the compute nodes and is thus running within a secure environment already. And yeah, the Slurm job submission script itself will run on a compute node. Then the with local storage is just indicating how Spindle gets around having, how Spindle solves the problem of having a massive hit on the IO server. And this is because things like libraries and library locations are going to be cached locally in the node memory. And so this is the path, the /dev/shared memory area. So that's just telling Spindle where to cache items. And so there was a little caveat with installing Spindle on ARCHER2, mainly to do with for versions of Slurm, which is the batch management system on ARCHER2. For versions of Slurm later, the 20.11, that interfere and prevent Spindle from launching their own daemons to manage the caching of libraries and library paths in shared memory. So this applies to both ARCHER2 and Cirrus, because they have versions of Slurm later than 20.11. And so the workaround is to build with the with-slurm-launch option. And then in addition, when you come to run your code, you have to pass the -- overlap option to the srun command. So and on Cirrus, there's a bit of a difference, because with the local storage, you have to specify a /temp, and because on the dev shared memory folder, the user doesn't have the execute privilege. And these instructions that I've just kind of flashed up, they're kind of fully laid out within a GitHub build instructions repo that EPCC manage. So basically, just to recap, I think it was mentioned on the slide, but I didn't maybe say it out loud, that when you come to run Spindle with your Python code, say that is doing lots of import statements, what Spindle will do will monitor the libraries or the Python packages that you need to load and ensure that they are cached in node local memory. So basically only one rank from each node will actually be hitting the IO server. And then all the other ranks on that node can just use the cache data. And so the way it's run is quite straightforward. We just have to load the Spindle module. There's a Spindle module essentially installed on ARCHER2. And in this case, we're just running on one node. It's a fully populated node, so there are 128 ranks. So this isn't particularly at scale. So your srun command, it has an extra sort of prefix part to it, and this is when you run Spindle, you indicate the batch system that you're using, Slurm, and then you have a Python prefix to give the path for your Python installation. This prefix path, you can have more than one path. You just have to separate each path by colon. So if you had your own locally installed Python environment, you might want to extend the prefix string. So there you go. There's an example of Spindle being used with a real-world code called FireDrake. It's an automated system for the solution of partial differential equations using the finite element method. So this works in the way that I described, in the way that Python is used typically on HPC. You have a Python front end, which allows the user to express what they do in terms closer to the problem domain, but then under the hood, it will take that and then convert from that representation, from that description, the necessary kernels that will then do the computational heavy lifting. So in this case, it's C code that is compiled for ARCHER2. And then the plot is just showing the impact of using Spindle. So the solid blue line is without Spindle, and you can see as you increase the number of nodes to above 128, so that basically ramps up the import time, and you can see that it's going to increase even more as we go above. If you increase the number of nodes even more. And so when you're using Spindle, it reduces, it mitigates that kind of rapid rise in runtime. And with FireDrake 2, I think at various points during a run, there will be Python imports that take place. So this is a problem that's impacting FireDrake all the way through the run. So that's Spindle. There's just a bit more to say about. There's an extra tool called Pynamic, which you can use to test Spindle's ability to handle dynamic linking for the loading, for the level of loading requirements that you're interested in. So what you do there is you build Pynamic for a particular library or Python module count, and then that generates build will generate a number of dummy libraries that are built and installed locally, and then you can run the custom dynamic benchmark without Spindle to see what kind of benefits it provides for the sorts of module load, Python package load that you are interested in, or that is pertinent to the code that you intend to use. So that's Spindle, and there's instructions on how to use Dynamic in the same GitHub repo that I mentioned earlier with regard to the Spindle compile and run instructions. So moving on to the next lightning talk, so this is concerning machine learning benchmarks, and for a while now we've supported the use of TensorFlow and PyTorch on Cirrus and more recently on ARCHER2. And one of the problems with the setup on Cirrus was because typically the users will want to use the GPU nodes, and then they would want to use multiple GPU nodes, and an issue was trying to make sure the MPI library was built such that it was compiled for the GPUs and allowing the GPUs to communicate efficiently. And so there's quite a software stack involving the NVIDIA SDK, OpenMPI, and MPI for Pi, and also other packages such as Horovod, which allows you to distribute a machine learning workload across multiple nodes. And another issue was trying to find a decent benchmark, actually, a decent test case that would allow you to be sufficiently heavyweight to test on multiple nodes. We were using we used the MNIST, the handwritten digit recognition test case, which wasn't really large enough to go beyond one node. We had ImageNet that we used, but that was actually using TensorFlow version 1, so that game wasn't great. So we were very pleased to learn about something called MLPerf, which is a group that maintain a set of machine learning benchmarks that are close to what people are using machine learning for. So these are close to real world problems. So these are realistic use cases, and if our software stacks can run these well, then we could be sure that they would work, or more certain that they would work for what users would want for. So in this lightning talk, I'm going to talk about CosmoFlow, which you may have guessed uses TensorFlow, but there are other benchmarks that MLPerf provide. The other three use PyTorch. There's a link that you can explore. I should mention that MLPerf is a product of the ML Commons Consortium, and a few other links to follow if you're interested. So CosmoFlow is all about trying to train a deep neural network such that it can recognize cosmological parameters from the output of cosmological simulations. So on the left, you've got this image. It's actually a subvolume taken from a full 512 megaparsec simulation of dark matter in the universe, evolved over 3 billion years to a redshift of 0. So I imagine a lot of this cosmological simulation work is changing quite a bit right now in light of the recent observations by the James Webb Telescope. But that's beyond the scope of this talk, so I mentioned that. So there are a few units I've just mentioned that you might not be familiar with. I'll just explain, like the parsec is defined as a distance at which one astronomical unit subtends an angle of 1 arcsecond. So an astronomical unit is the distance between the Earth and the Sun. So 1 parsec works out to be about 3.3 light years. And the dimensions are so huge that they're actually scaled by the Hubble parameter, this lowercase h. So what, just go back. So we're trying to train the deep neural network to recognize these 3 cosmological parameters, and I've got them in order of how well I understand them there, those 3. So the idea is that you first run many cosmological simulations for a variety of parameter values constrained by observations of the cosmological microwave background, and that's data taken by the Planck mission. So this is work that's already been done. We already have the test data sets. So the idea is that these simulations are run basically as a parameter sweep that remains within the error bars of the observations that were made by the Planck probe. And then all of that output data is then sliced into 128 cube voxel subvolumes, and then used as input to the CosmoFlow deep neural network. And so we have a real kind of full fat data set, a large data set that will stress the machine, and we'll have an idea of how well it holds up and which options and tweaks you can make give you the best best performance boost. So we have fairly a large training set of over 500,000 images, and a testing and validation test sets too. So to run CosmoFlow is quite straightforward. Once you've got the CosmoFlow repo cloned within your local area in ARCHER2, you just need to load one of the centrally installed TensorFlow modules, and then you specify a few options, a few environment variables, and then you would pass some settings to the CosmoFlow train Python script. So here, I mean, I just explained a bit more. Here we're launching across 32 nodes, and we are running 8 MPI ranks per node and 16 OpenMP threads per MPI rank. So each MPI rank is running within a NUMA region, so that kind of improves the efficiency of the memory accesses, because if you're within NUMA regions, all of the memory accesses can be nicely segmented. So I'm going to explain a few of the options that I've set here. So there's this TF enable 1DNN options environment variable. So 1DNN refers to the Intel 1 API deep neural network library. So within TensorFlow, there are a number of hashif-def guards or something equivalent to that, where if this environment variable is enabled, those code segments are activated or executed, and those are kind of known to run fast on Intel processors. But it turns out that they also run fast on AMD processors too. In fact, we get a 12 times speed up compared to when that option is disabled. The other, the various parameters that are passed to the train script, which is provided by the CosmoFlow repo. So the deep neural network is represented by TensorFlow as a graph, and there are two ways in which parallelism can be introduced. So within a node of the graph, it might be possible to parallelize the work that takes place there. So the number of threads assigned would be the value of the intra-threads setting, or within the graph there are separate nodes that can be run concurrently, and the available thread count for that is the value of the inter-threads setting. So here we set it to 0, 0, because when you do that, you're telling TensorFlow to choose the optimal values itself, which is probably the best thing to do, because what the optimum values will vary from network to network, depending on your use case. So we did this on ARCHER2. So like I said, and we found that when we ran such that we had 16 OpenMP threads per MPI task per node, that we got a 7 times performance boost. And then we tried with an alternative to Horovod, and Horovod is a Python package that allows you to distribute machine learning workloads across multiple compute nodes. So there's an alternative to this provided by HPE Cray called their deep learning plugin, and we used that. That required using an old version of TensorFlow, but we got roughly the same sort of performance, the same sort of run times. And what I mean is we just ran for 10 epochs, took about 3 hours and 20 minutes, and we ran across 32 nodes. And we were just interested in measuring the benefit of making various changes to the environment, so setting certain environment variables or using a different alternative to horovod, or changing the CPU frequency. So when we ran with the frequency set to 2.25 gigahertz, which is actually a boosted setting, so it might have been higher than that when it runs. We got a runtime boost of 8%, but a similar increase in the energy use. So we've kind of explored that, and that's been very useful for us to have access to real-world test cases with decently sized data sets. And Eleanor Broadway has done all this work, so thanks for her and these findings. And she's also used CosmoFlow on the Cirrus nodes. If you're interested in learning about that, you can contact Eleanor on the email address shown. So that includes that lightning talk. So let's move on to the third one now. And this is about roofline models or roofline plots that have been generated using Intel Advisor. So the roofline plot is a succinct way of just evaluating the performance of your code and understanding the theoretical maximum performance that your code might achieve. It kind of implicitly recognizes that the performance of your code depends on which subroutine or which function or which loop is executing at the time. So it's not you don't necessarily have a performance rating that implies to the entirety of your code. It's much more useful to see how the performance changes as control moves within the elements of your code as control passes from subroutine to function and so on. So it's a two-dimensional plot, and on the vertical axis you have your performance, which is the gigaflops per second, and then the horizontal axis you have the arithmetic intensity, which is all about the number of floating point operations you do per byte moved or per byte access from memory. So if your arithmetic intensity is low, so in other words, you're having to access a lot of data before you can do any floating point operations, you'll find that your memory bounding, your performance is limited by the bandwidth of the memory that you're using. If, on the other hand, you have a high arithmetic intensity, so you're doing lots of flops, lots of floating point operations, and not having to access the memory so much, then you're limited by the speed of the processor. You are compute bound. And so the way this works, I mean, you have different points that appear under the roofline, and each point will be associated with a particular part of your code, a subroutine or a function. And then you can go further, you can color code those points or make some of those points larger, depending on how much of the overall execution time that function or subroutine is responsible for. So it's a nice 2D view representation of the performance of your code, how it varies throughout your code, and it's just a simple two-dimensional plot, really. So if you wanted to maximize the compute performance, if you were, say, underneath the straight part of the roofline, you would do things like vectorize your code. You might use fuse, multiply, add instructions. If you were under the slope part of the roofline, if you're memory bound, you might think about using lower level caches because they would have a higher bandwidth, being closer to the CPU. You might think about numer allocation, avoiding the use of non-contiguous memory. Alternatively, if you wanted to move out of the memory bound regime into the compute bound, so you would have potentially a higher theoretical performance available to you, you think about minimizing the data movement or exploiting cache reuse. There are various ways in which roofline plots can be extended. So when you run on a system, you have more than one type of memory available to you. You'll have cache memory too, and different levels of cache. And so as you go up from L2 to L1, it's closer to the CPU, so the performance creeps up, and so these slopes move up to the top left. Another way is that you can categorize the sorts of floating point operations you are doing, and there will be different theoretical maximum performances that you can hit for those. So that could be broken up here according to the precision, whether it's single or double, or fuse, multiply, add, or straightforward add. So I just talk about how you can get a roofline plot using Intel Advisor on Cirrus. Now, Cirrus uses Intel processors, so it's quite straightforward. We've got a bunch of essentially installed Intel modules, TCL modules that you can then load. So the suitable compiler, for example, or an Intel MPI library, and you can just specify your compiler and flags like so. And then when you come to run your code, you would then need to load the Intel Advisor module. So here we're just running on one node, 36 tasks on the node, so using all the CPUs. When you've loaded Advisor, you then need to run a source and an initialization script. And once that's done, you set up a directory to hold the results that will be created by Intel Advisor. And then you do your srun command, or you actually need to do 2 srun commands. So things are a little more involved here. You can see each command is made up of 3 parts. You've got your srun part where you specify the srun options that you are using. You then got the Intel Advisor command line and all the arguments there that you need to specify. And then finally, you've got the application and its options that you are interested in profiling. So the first srun command is when you do a collect, you do a survey. You do a survey to collect the initial performance data, and then you do a collect for the trip counts. So that's the number of times loops will iterate, and then you want to collect the flop data. So that's floating point and integer operations, and also memory traffic. And then you can also collect information about the call stacks. So it may be interesting to know if there's a hot loop within your code where a lot of time is being spent. You can see where it appears on the call stack as well, because it may be possible to make changes to the calling subroutine to make that loop run faster. So, and then you indicate the folder where all the results will be collected. Now, the visualization tool for Intel Advisor is very rich, so it's best to run in an environment that's as responsive as possible. So it's best to install it locally on your local machine, and you can do that for the Windows, Linux, and Mac environments. And then the other 2 links are just useful for documentation, so for the Intel Advisor user guide, and there's also something called an Intel Advisor cookbook, which lists a set of different profiling scenarios that you might be interested in. It also includes a section running Advisor on HPE Cray systems. So when you've got Intel Advisor, the visualizer or the UI installed locally, and then you've run Intel Advisor on Cirrus, you've collected the results and you've downloaded those results, you can then open them up within your local Intel Advisor. You do file open result, and then you select from the results folder that particular file. And then when you've done that, you get a list of all the ranks that were profiled. So in this particular example, there'll be 36 ranks. You double click on the rank that you're interested in, and then you get this type of plot. So this is the cache-aware roofline plot. And you can see you've got your L3, L2, and L1 rooflines along with the memory roofline. And you've got various categories of compute performance that make up the different horizontal lines that you see. And all of these circles that you can see here, they represent different elements within your code, loops, functions, or subroutines. And these are plotted with respect to the rooflines. So the circle colors and the diameters of these points correspond to the runtime percentage that those parts of the code are responsible for. So green is between 0 and 1%, and yellow is between 1 and 20%, and red is greater than 20%. So it's the red one is where you would think of focusing your efforts to improve the performance of your code. And it's a nice dynamic UI, because if you move the mouse pointer over any particular point, there'll be a pop-up that appears that tells you which part of the code is represented by that point. So that's a crucial bit of information. And here, this red dot corresponds to a loop within a subroutine called MKLF_F2. So yeah, you've got some various stats, such as the memory, traffic, arithmetic intensity, and elapsed time. And also it just plots a dashed line that's going vertically straight up, which then shows you the theoretical maximum performance you can get. And where that point is, it's limited by the L1 cache bandwidth. But you can see you're quite close to the compute performance bandwidth, and you might think about moving that to the right. There's various options there where you can think that suggest how you might go about improving the performance of that loop. To do the same thing on ARCHER2 is a little bit more involved, because ARCHER2 uses AMD processors. But what we have, a colleague of mine, Adrian Jackson, has provided a set of Intel One API module files, which you can load up by using this module use command, so that they are available to you. And then, as with on Cirrus, you can just load the relevant compiler modules and MPI modules and then build. There is a caveat here in that you, I just get my, I don't know if you can see a mouse pointer here. It was working earlier. But when you come to source various scripts associated with the Intel compiler and the Intel MPI, you need to specify other options, such as here I'm specifying an MPI OFI internal equals 0. So OFI is a communications interface that I just want to make sure I don't use the interface that's provided by the Intel One API modules. I want to use libfabric, which is set up by HPE Cray, which is the one to use when I'm running on ARCHER2. And I also need to indicate a similar thing here when I'm specifying the MPI_fabrics environment variable. So you need to do a few extra things. And then when you've done that, it's pretty much straightforward to then submit your job such that you will profile with Intel Advisor. Again, you will need this module use command to get the modules that Adrian Jackson has set up. Then you load the Advisor module, you initialize it, and then you're ready to go in pretty much the same way as you do on Cirrus. Now, there's an extra option that you need for the srun. You can see here, it's got it in bold in the first srun called, this is the MPI equals PMI2. You just need to make sure that you're using the process management interface suitable for Slurm running on ARCHER2, and then that should work. And having done that, this is the kind of the plot you get. Now, unfortunately, you don't get the cache rooflines, and this is despite the fact that you do have the option when you use the Intel Advisor command line tool, the one that you specify in the submission script. You do have the option of using a cache config option, where you can give the full details of the 3 level of caches on ARCHER2, but unfortunately that doesn't make any difference. There is the option though of exporting the roofline to HTML file, and when you do that, it preserves the responsiveness or the dynamicness of the roofline plot. And what I mean is that when you do things like move your mouse pointer over a particular dot under the roofline, it will pop up the details that will explain which part of the code is being represented by that dot. So you still have that within the HTML export. So now there's work in progress where we're going to, I'm going to run the stream benchmark to nail down the bandwidths for the level 1, level 2, level 3 caches on Archer2. When I have that information, I can then hand edit the HTML exported file to put the cache rooflines on there. And you can see that some of the green points that have been plotted here are actually above the memory slope and are presumably limited by either the level 3 or level 2 cache bandwidth. So there's just a bit of work that we'll do there, and hopefully we can make this convenient for users such that they can take an exported HTML file and just run a Python script on it to get the Archer2 cache lines. So now moving on to my last talk. So this is about using OpenMP to offload to GPU. And this is using OpenMP version 5.1. And this example is about a Fortran code on Cirrus. And I was interested in using OpenMP offload because it's hardware diagnostic to some degree. So the changes I need to make to my code to use OpenMP offload should then be applicable to running on an AMD GPU, for example. And hopefully we should have AMD GPUs installed on Archer2 for the new year. So I'll just talk a bit about the GPU hardware that's on Cirrus. There are 36 GPU nodes, and each, a bit of a typo, so each node has 4 NVIDIA Tesla V100s. They have about 16 gigabytes of high bandwidth memory. They have a number of cores, and these cores are organized in terms of streaming multiprocessors, or SMs. And so on a GPU, these streaming multiprocessors can be thought of as almost a mini compute node, because each one will have a number of cores. They have registers and some cache and so on. I mean, they don't have their own RAM, I don't think, but that's so there's opportunities for lots of parallelism with a GPU. And there's a schematic of the architecture, and outlined in white is one streaming multiprocessor, just to give you an idea of the scale. So the Cirrus programming environment that's applicable here is there are a number of centrally installed TCL modules. I've got the NVIDIA SDK, and I need to have the module that doesn't contain its own MPI library, because I need to provide that separately. That's the OpenMPI module. And OpenMPI is useful, it being open source. We have full control of the way it's built, and we can build it such that it is tailored to a specific CUDA version, a CUDA version that is known to be compatible with the GPU device driver that's currently installed on Cirrus. And then we need a special GCC compiler, one that is linked to the NVIDIA SDK, and so supports GPU offload. And then when we come to compile the code that we're interested in doing offload for, we need to specify a few more options. So we've got one to enable compilation of code for NVIDIA parallel thread execution environment. That's the MVPTX option. And then the next option is just provides a list of libraries which need to be provided as offload targets. So we got the basic libraries there, like the libm, the elementary mathematical functions library, and libatomic, which is the runtime library for atomic memory operations. The MVPTX-none is a little bit confusing because it's almost like you're switching it off, but I think none just implies that we're using a vanilla flavor of MVPTX. The use case that I'm going to do offload for is for something to that I worked on a project recently for the British Geological Survey, and it involves a code called the World Magnetic Anomaly Model. And what this code does is it takes observations of the crustal magnetic field, and then it interpolates from those observations a spherical harmonic model that then gives you the vector magnetic field globally. So it's doing a massive interpolation, basically. So that has various usages across research and as an aid for exploration of mineral deposits. So this is the code. So this is a snippet, a part of the code. So obviously I ran the anomaly model and I profiled it and found out where execution time has been spent, which loops are hot, and appreciate there's lots of parameter names that I'm just throwing up on the slide here. So I try and relate this back to the background that I just described. So the MB integer is merely the number of coefficients required by this spherical harmonic model that I'm trying to interpolate. And then SH degree is the maximum degree of my spherical harmonic model, how detailed it is, basically. And then the BC array is my current coefficient set. So as the code runs, it searches through different coefficient sets to find the one that best matches observations, and then also obviously gives me the spherical harmonic model of the right degree. And then a variable such as nloc points, number of local points, is the number of lithospherical crustal positions that are being assigned to MPI rank. So each rank is going to have to go through its assigned points, its geographic coordinates, and work out what the model predicts will be the magnetic field for its points, and then how well does that compare to observations. So how do we offload this? So well, we start to put in some OpenMP directives. So I'm just got a few more points just to give you an idea of the sizes involved. So crucially, the maximum bound of the loop nloc points is 36,000 or so. So that means that there's enough work to be divided amongst the number of streaming multiprocessors that are on a GPU. And then you've got the various arrays that then need to be written to the GPU memory. And those are indicated there. So these are the OpenMP directives you would use to do offload. So we specify the target teams and distribute parallel loop, parallel do. So what we're doing here is we're taking the iterations within the loop, and they're going to be distributed over various teams that are running on the GPU. And by teams, each team is basically assigned to a different streaming multiprocessor on the GPU. And then before we start this, we've got to download to the GPU the various data that it's going to need, the various integers and arrays. So this is the purpose of the map2 directives. And then we've also got to have data that comes back from the GPU, and this is the map from, and that involves this XYZF array. The size of that array is the number of points that have been assigned to the rank, and what that array holds is basically the differences between the magnetic field strength implied by the model that we're trying to calculate and the observations. So the smaller those differences, the closer we are to finishing. Now, it turns out that there are some parts of the data that are downloaded to the GPU that don't change once those arrays, once the D2A array, for example, or the PPOS array has been set up during the starting phase of the code. It never changes during the actual algorithmic part of the code as it iterates towards a solution. So what we need to do is really only download those to the GPU once, and this is the purpose of this OMP target enter data section. And so I take advantage of, in Fortran, I've got the save attribute, so that the first time the subroutine is called, that's set to true, and that will then kick off all of these map2s for the D2 array and the PPOS array. But as soon as that's completed, first call is set to false, and so that will never happen in subsequent times when this loop is executed. And so for the loop itself, I just need to put in the current coefficient set for the spherical harmonic model, which obviously that will be changing as the algorithm iterates. And then obviously I need to get back the differences too. And then one thing that's essential here is I need to set, I need to call a OpenMP function called OMP set default device. And what that does is link my MPI rank to a particular GPU on the node. I've got the mod operator here such that you can have more than one rank on a GPU or associated with a GPU. But I mean, if you don't do this, then actually all the ranks will just use the same GPU on the node. And so you won't get a performance improvement in that case. Yeah, so I was just explaining the code snippet above is suitable for a single node job and would accommodate having multiple ranks per node. If you wanted to run a multiple GPU nodes, you would need to use a node local rank here. There are other attributes you can set for target teams. You can specify the number of teams, or you can specify the number of threads that are available to a team. So the number of threads will basically be based on the number of cores or CPUs that exist within a single streaming multiprocessor on the GPU. In practice, though, I found that it was not necessary to set these because the OpenMP will choose the optimum values automatically. But I just thought I'd mention them. So, okay, I did a test for a simple use case for a fairly low spherical harmonic degree of 200. When I ran on just 4 ranks from a single node, my fastest execution time was just over 1,000 seconds. Then when I offload that loop in the subroutine that I've shown on the previous slides, the execution time improved to 452 seconds, a speed of about 2.3. So there is actually another hot loop within this code that I need to offload, one that requires an element-wise array reduction. The loop is more complex, and so there's a bit of extra work to see if I can get the OpenMP offload to work in that situation. So it's ongoing there. But when I move up to higher spherical harmonic degrees, and these are the sorts of degrees that the BGS, the British Geological Survey, will run, 1414 2000, then the memory requirement increases a lot. It goes as a square of the harmonic degree. And then there'll be a need to perhaps think about pinned memory. And pinned memory, also known as page locked memory, is just a type of memory that is locked in physical memory and cannot be paged out to disk. So just accessing that memory is a little faster for the GPU. So there's also the point to make that the GPUs on Cirrus are rather old. They're a couple of generations behind the NVIDIA H100s. So I think you would get better performance using NVIDIA A100s or the AMD MI210s, which we should be getting on ARCHER2 for the new year. So that concludes my talk. I don't know if anyone has any questions.
Okay, well, thank you very much, everyone, for attending. Thank you, Michael, for very interesting talks. And
yeah.
bye just now.
Okay, then. Thanks. Bye.